In this video, we're going to learn about two types of special right triangles, the 30, 60, 90 right triangle and the 45, 45, 90 right triangle. The 45, 45, 90 can also be called an isosceles right triangle because when you have two angles that are the same, you also have two sides that are the same. And notice in this case, it's the two legs of this right triangle that are congruent. Before we get started, let's review rationalize in denominator because that's one skill we'll need to know how to use. In mathematics, we are not allowed to leave square roots in the denominator, and in situations like these, an easy way to get that square root out of the denominator is to multiply both the numerator and the denominator by whatever square root is in the denominator. So for this first one, we'll multiply by the square root of 3 over the square root of 3. Now notice we're multiplying this first fraction by another fraction that equals the number 1. So we're not changing the value of this fraction. So let's multiply straight across the top and bottom. 1 times the square root of 3 is just the square root of 3. Square root of 3 times square root of 3, well, that equals the square root of 9. But the square root of 9 equals 3. Now, super important, these 3's do not cancel because the 3 in the numerator is not really a 3. It's a square root of 3. Now, notice here, this wasn't a coincidence. This will happen every single time. When we multiply a square root by itself, we get that same number, but without the square root sign. So if we had multiplied the square root of 17 by the square root of 17, that would just equal 17. Let's try the same thing on B. We're trying to get rid of the square root in the denominator. So we'll multiply by whatever square root is in the denominator, in the top and the bottom. Multiply straight across the top and straight across the bottom. And once again, notice we cannot cancel those 2's because that's not really a 2. Now sometimes there's some simplifying we'll need to do after we rationalize the denominator. So once again, we'll multiply by the square root of 3 over the square root of 3. And so we get 3 times the square root of 3 over 3. Now these 3's do cancel because they're both regular 3's. And 3 divided by 3 equals 1. And sometimes there's even more simplifying. So let's take a look at an example where we need to continue simplifying. So we'll multiply straight across the top and bottom. Now here we can divide both the 10 and the 2 by 2. So let's go ahead and do that. All right, 10 divided by 2 is 5. Square root of 2 just tags along. And 2 divided by 2 is 1. And we don't care about 1's in the denominator, so we'll just rewrite that as 5 times the square root of 2. Now, bear with me for just a minute or two while we go over how to find the missing sides the long way, because I really want you to see where these shortcuts come from. It's not just some magic trick. Right, here we have a 45, 45, 90 right triangle. Now we know this third angle is 45 degrees because the angles in a triangle have to add up to 180, so that's how it works out here. Now when you have two angles that are congruent, the sides across from those angles are also congruent. So this other leg also has a length of 4. Now when we have a right triangle, we know two sides, we can use the Pythagorean theorem to figure out the third side. So let's go through a squared plus b squared equals c squared to figure out the length of m. I'm just going to switch sides here. We get m equals the square root of 32. Okay, and when we have square roots, we need to simplify those by factoring out any perfect square roots. 32 equals 16 times 2, and 16 is a perfect square root. So I'm going to rewrite this as the square root of 16 times the square root of 2, which equals 4 times the square root of 2. So we notice that this side, the hypotenuse, equals 4 times the square root of 2. Now what we're going to be talking about in a moment is how this 4 here is not a coincidence. This is going to be part of a pattern that we'll use to quickly find the lengths of missing sides on 45, 45, 90 right triangles. And it basically just comes from the Pythagorean theorem. Okay, we'll be using the Pythagorean theorem here also, but notice we only know the length of one side right now. So first, we're going to look at how this is half of an equilateral triangle. So I'm going to sketch an equilateral triangle with three congruent sides. Now when you have three congruent sides, you have three congruent angles. And since triangles equal 180 degrees, these angles all must be 60 degrees. Now if we drop an altitude down, that altitude will bisect this angle up here, so these will both be 30 degrees. And this will also be a right angle. So notice that when we have a 30, 60, 90 right triangle, it's half of an equilateral triangle. Well, that's helpful because that means that if we know one side of, or the hypotenuse of the 30, 60, 90 right triangle, then the leg right here, the shorter leg, will be half of that because it's halfway across, or it's half of 6 in this case. Because we know this side has a length of 6, so this little part must be 3. All right, and now we can use, remember, we're doing this the long way, or almost to the shortcuts here. We'll do the Pythagorean theorem quickly to figure out the length of the missing leg. Now, once again, we can factor out a perfect square root from 27, because 9 times 3 equals 27, and 9 is a perfect square root. So the square root of 27 equals 3 times the square root of 3. The square root of 9 turned into a 3, and the square root of 3 just tagged along. All right, so when we had a 30, let's see, this angle is 30 degrees. When we had a 30, 60, 90 right triangle, we had a hypotenuse of 6. The shorter leg was half of that, and the longer leg turned out to be 3 times the square root of 3. Now, it's not a coincidence that this 3 that was here also appears here. Okay, we're ready for our shortcuts. All right, here's a summary of the shortcuts with a 45, 45, 90 right triangle. The hypotenuse always equals the length of the leg times the square root of 2. And in a 30, 60, 90 right triangle, the hypotenuse is always twice as long as the short leg, and the long leg is equal to the short leg times the square root of 3. That's what we saw in the previous examples with the Pythagorean theorem. Okay, let's see how this works. So we're going to solve for x, and we're not going to convert our answers to decimal form, and we are going to rationalize the denominator if necessary. Okay, we have a right triangle here. We know it's a right triangle because of the box. One of the angles is 45 degrees, and because a triangle equals 180 degrees, this other angle must also be 45 degrees. So we have a 45, 45, 90 right triangle. Now, in that type of right triangle, we know that both of the legs will be congruent. They'll be the same length. And we know that the hypotenuse will be the length of one of the legs multiplied by the square root of 2. And that's all there is to it. That's just the shortcut that comes from the Pythagorean theorem. Okay, now here, the setup is a little bit different. It almost looks the same. We have a 45, 45, 90 right triangle. But this time we know the hypotenuse instead of one of the legs. So we need to work backwards. So remember, to get the hypotenuse, it was the length of it was the leg multiplied by the square root of 2. So to go backwards, we're going to divide by the square root of 2. So in this case, x will equal 10 divided by the square root of 2. Now we can't leave our answer like this because we're not allowed to leave square roots in the denominator. So let's rationalize the denominator by multiplying by the square root of 2 over the square root of 2. And 10 divided by 2 equals 5. So this is just 5 times the square root of 2. All right, and that's how long this leg is. Okay, let's look at 30, 60, 90 triangles now. So here we have a right triangle. One of the angles is 60 degrees. So in order to have the angles add up to 180 degrees, the third angle must be 30 degrees. So we do have a 30, 60, 90 right triangle. And in a 30, 60, 90 right triangle, the hypotenuse is always the short leg multiplied by 2. So in this case, z equals 28. And once again, here we have a 30, 60, 90 right triangle. And, well, see, in this case, we don't care about the hypotenuse. The hypotenuse is always across from the right angle. We're interested in the other leg. And the length of the long leg is always equal to the length of the short leg multiplied by the square root of 3. So this long leg will have a length of 16 times the square root of 3. All right, once again, we have a 30, 60, 90 right triangle. And we know the length of the long leg, and we need to figure out the short leg. Well, the shortcut tells us that to get the long leg, we multiply the short leg by the square root of 3. So we're working backwards. So we're going to divide by the square root of 3. All right, so m, that's the short leg here, must equal the long leg divided by the square root of 3. We can't leave square roots in the denominator, so let's go ahead and rationalize the denominator. And we get 4 times the square root of 3 over 3. We don't cancel these 3's because that's not really a 3. Once again, we have a 30, 60, 90 right triangle. And this time we know the hypotenuse, and we're looking for the short leg. Well, to get the hypotenuse, that will equal the short leg multiplied by 2. So this is twice as long as a short leg. So in other words, to work backwards, we need to, instead of multiply by 2, we divide by 2. So z will just equal 6, which is 12 divided by 2. Okay, once again, we have a 30, 60, 90 right triangle. We know the hypotenuse. That's across from the right angle. And we are looking for the long leg. Now, there is no shortcut to tell us how to go from the hypotenuse straight to the long leg. So in this case, we're going to take 2 steps. We're going to go from the short leg to figure out, we're going to go from the hypotenuse to figure out the short leg. And then once we know the short leg, we'll use that to figure out the long leg. All right, in a 30, 60, 90 right triangle, the hypotenuse is always twice as long as the short leg. So 26 divided by 2. So this short leg has a length of 13. Now the long leg is always equal to the short leg multiplied by the square root of 3. Always the square root of 3. So z is equal to 13 times the square root of 3. Okay, we'll need 2 steps here again because there is no shortcut to help us go from the long leg straight to the hypotenuse. We need to figure out the short leg first. All right, the long leg equals the short leg multiplied by the square root of 3. So to work backwards, to get the short leg, we will divide by the square root of 3. So that would be 5 divided by the square root of 3. Right, now in this case, I think we'll leave the square root in the denominator for now, and then we'll rationalize the denominator later. Okay, now the hypotenuse, that's this side here. The hypotenuse is always straight across from the right angle. That will equal the short leg multiplied by 2. So we have the short leg, 5 over the square root of 3, multiplied by 2. Now when we multiply a fraction by a whole number, we can always just put a 1 underneath that, that whole number, multiply straight across the top and bottom. And now we need to rationalize the denominator. So we'll multiply by the square root of 3 over the square root of 3. And there we have it. The hypotenuse equals 10 times the square root of 3 over 3. I hope you found this lesson about the shortcuts we can use with special right triangles helpful. This is Mr. Ela, signing off.